This virtual lecture is on just-in-time systems, which are also known as lean or lean operations. So Shigeo Shingo, who was one of the godfathers, so to speak, of lean operations, characterizes just-in-time or lean as producing what is necessary, when it's necessary, and the amount that's necessary. Another way to think about that is that producing stuff that's unnecessary or producing too much or at the wrong time, especially well in advance of when it's needed, is waste. So we can also think about the goal of just in time as the elimination of all waste. This applies to independent demand level items that the company may make or provide to its customers, whether or not those customers are consumers buying an end product or whether we're in a business context. So the idea here would be to deliver finished goods that are demanded by the market exactly when the market needs them. So that sort of implies that we also, at the dependent demand level, produce and purchase components and raw materials, the things that are required for our finished goods, when they are needed in order to make finished goods. Not too far ahead of time, not in excessive amounts, and certainly not the wrong things. So let's start out talking about the independent demand level. And when we're talking about that, the main technique that we need to understand is uniform plant loading, also known as mixed model production. Generally, if we think about product or family of products, the market demands a mix of those products. So the idea is that we try to make products in a mix. In other words, we make products in very small batches rather than in large batches, and that allows us to produce each different item in a product family frequently, as opposed to producing items in large batches infrequently. So here's an example. On the top half of the screen, we've got what the market requires. And you can see that, on average, this could be a production forecast, for example. The market requires 10 units of A, 20 units of B, 5 units of C, 5 units of D, and 10 units of E every week. So traditional operations management would probably tell us that on Monday, for example, we go ahead and we produce all the A's in one big batch. So we have 10 units of A's that we're going to produce on Monday, and we need 20 B's. So if we can produce 10 units a day, we would produce a big batch of B's, and that would consume 2 more days. And then you can see correspondingly what happens to the rest of the week. We produce one batch of each item. Down here on the lower part of the screen, we can see mixed model or level or uniform schedule. And you can see it's quite different. On Monday, we produce 2 A's, 4 B's, a C, a D, and 2 E's. So we produce 1/5 of what's needed throughout the week. On Tuesday, we do the same thing. Wednesday, we do the same thing. Thursday and Friday, we do the same thing. So you can see here, as the name suggests, the schedule is uniform. The schedule is mixed. The schedule is level. We're trying to produce what's needed every day. There's a lot of advantages to this. Probably the biggest advantage is that customers don't tend to buy, all their A's on Monday and all their B's on Tuesday and Wednesday, and so on. Customers generally, buy a mix of products, and here we're mimicking that market demand much more closely. So that'll allow us to have, among other things, lower inventory and possibly the opportunity to adjust production if production turns out to be different than what we forecasted. If on Wednesday we find out we don't seem to be selling as many A's as we thought we were selling, well, it's kind of too late to do much about that because we've already committed to making all the A's. We've made all the A's back on Monday. Could even take this a step further. For example, instead of producing 2 A's and then 4 B's and so on a given day, we could try to break it down as far as possible, which we can see right here. We could produce 1 A, 2 B's, C, and E, and so on every day. So if we sat at the end of the production line, this is the sequence that we would see things coming off the line. We see this in the U.S. stroller reading, in particular if we compare Exhibit 7 to Exhibit 8. Exhibit 7 is the kind of old way of doing things, the pre-JIT way of doing things, and Exhibit 8 is the master schedule that they envision with JIT. In Exhibit 7, of course, they're producing in large batches. In Exhibit 8, there's smaller batches, and each model is produced more frequently, just like we saw on the previous slide. We should point out that we don't really have true mixed model production in the U.S. stroller example because U.S. stroller is essentially retrofitting an existing system to try to become more like a mixed model system, but they can't get to the true sort of mixed model ideal because of some of the capital assets and equipment and things that they have. But they're getting closer, and as a result of that, they're going to have less finished goods inventory and accrue some other benefits as well. Okay, let's shift gears to the dependent demand inventory level. Remember that JIT's goal is to produce what is necessary, when it's necessary, and in the amount that it's necessary. And if we're talking about dependent demand level items, then that includes work centers within our operation that are producing materials for our consumption to go into other things, and also materials that we might buy from suppliers. If we're shipping our finished goods according to a mixed model schedule, or in very small batches at least, and we want to produce what's necessary, when it's necessary, and in the amount necessary when it comes to the things that go into those finished goods, then it follows that each work center, each supplier must produce or supply us in very small batches, or ideally maybe even batches of 1. And it also follows that downstream demand has to be tightly coordinated with upstream supply. So we need very tight coordination, very tight communication, very precise scheduling between consuming operations and producing operations. So let's start out with the first of those 2 bullet points at the bottom of the previous slide, and that would be producing in very small batches. Typically, in conventional operations, we tend to produce in fairly large batches at the dependent demand level, just like at the independent demand level, which was what we talked about before. One reason for that is setups. Traditional operations management views big batches as important to essentially prorate the costs of a setup across a lot of units. JIT kind of turns that on its head by kind of questioning the assumption that setups have to be long and expensive. In other words, JIT eliminates setups or reduces setup times, which essentially makes producing in smaller batches more economical. So let's talk about that a little bit more, and then we'll come back to the second bullet point on this slide. In the U.S. stroller example, they use the economic order quantity model. You may recall that the economic order quantity model looks at setup costs and holding costs, and the greater the setup costs, the more units one has to produce in a batch to reach a so-called economic order quantity or economic batch size. One of the things that U.S. Stroller does is they dedicate equipment to making one particular type of part, and that essentially eliminates the needs for setups, right? If a piece of equipment's only doing one thing, you never have to change it over from one job or one part number to the next. Another thing that they do is they use cells to make one or just a few items, again, eliminating the need for setups, or at least reducing the need for setups, because each cell is making a smaller variety of items. Sometimes it's not possible to eliminate setups or even reduce the number of setups, but there's another approach that we can take, and that's to reduce the time that it takes to do a setup. And the technique that is most commonly employed to do that is called single minute exchange of dies, or SMED. And this technique was honed in the automotive industry, where one of the things that they have to do is stamp out body panels on presses. So, in other words, they're stamping out things like fenders, door panels, and so on out of fairly thick steel with very big presses and very heavy dies. The die needs to be changed out each time a different body part is being stamped out. So there'd be one die for the left front fender, one die for the right passenger door, and so on. You can imagine those dies are pretty big, and changing them out is not trivial. It could take quite a long time. In fact, companies have found that they can take setup times literally from hours or sometimes even days down to minutes or less using this technique. A key step in this technique is understanding that there's two different types of setup activities. Two different types of setup activities: internal and external. Internal setup activities are activities that can only be done when the process is stopped. External activities can be done when the process is running. So, going back to our example of the dies in automotive, actually switching out the die, taking one die off the press and putting it on another press, can obviously only be done when that press is stopped. But there's lots of other things that we might conventionally do when the process is stopped that we could actually do when the process is running. For example, when we're stamping out one part and we know we're coming up on needing to stamp out a different part, we can go get the die for the next part, have it ready to go, clean it, and so on, before we stop running the first part. So the key steps in single minute exchange of dies are, number one, wherever feasible, we want to convert activities that we may be doing internally to externally. So any activity that we can possibly do while the process is operating, we want to do when the process is operating. And then the second step, after we've done step one, is look at all those remaining internal activities and reduce the time required to perform those remaining internal activities, so the process is stopped for an absolute minimum of time. There are a lot of applications of SMED beyond automotive and even beyond manufacturing. One example is the airline industry. Airplanes, of course, are very big, very expensive pieces of capital equipment, and when the airplanes are flying, they're making money. When they're sitting at the gate, transitioning from one flight to another, they're not making money. So anything that airlines can do to reduce that time, that non-value-added time that the airplane is at the gate, the better. So some airlines have gotten very good, particularly Southwest, at reducing that changeover time. If we wanted to apply SMED, think about the process. We want to think about activities that are internal and external, and think about externalizing every activity that we possibly can. For example, airplanes have food and beverage carts. Some airlines restock the food and beverage cart between each flight. They inventory it, and they bring required drinks and things like that to fill out the cart on between flights. But if you think about it, that's stuff that we could really be doing externally. We could really do when the airplane is in the air. In other words, if we had some extra food and beverage carts, we could have a food and beverage cart preloaded, ready to go, and when that airplane lands, we'd roll off the food and beverage cart that's on it, and we would roll on a new cart. And then that cart that we rolled off, we could fill up while the plane's in the air and put that cart on another airplane. We could also analyze the internal activities to think about how to reduce the time it takes to do those activities. Of course, getting the passengers on and off the airplane is something that's best done internally. We wouldn't want to try to do that when the airplane is still in the air. But there's things that airlines have done in the past few years to reduce the amount of time that takes. For example, years ago, airlines used to board people by row number, and eventually the airlines went to a zone system. In other words, on most airlines, there's a boarding zone printed on the boarding pass, and that apparently speeds up the process of getting passengers on the airplane and getting them seated. Of course, some airlines, particularly Southwest, have even gone so far as to eliminate assigned seating, and that also reduces the amount of time it takes people to get on board and get in their seats. Okay, so we've talked a little bit about how JIT reduces or eliminates the number of setups through things like dedicated equipment and cells, and we've talked a little bit about how JIT reduces setup times using techniques like single-minute exchange of dies technique. So those are two ways in which JIT would view small batch production as more economical than it might otherwise be viewed. The third important concept with regard to small batch economics is the cost of carrying inventory. And JIT proponents would argue that the costs of carrying inventory, in particular work in process inventory, are higher than are conventionally recognized. In particular, high inventory causes long lead times, and high inventory can reduce quality and increase variability. So let's start out by talking about the connection between inventory and lead time. Here's an example of a very simple value-adding system. We've got two different work centers, Work Center 1 and Work Center 2. And material has to go through Work Center 1, and then it goes to Work Center 2, and then it's completed. And you can see that this is a fairly high inventory system. We've got a lot of work in process inventory. Let's think about what happens to this unit here. Before this unit can be processed through Work Center 1, it's got to wait for all these other units that are in line to be processed. So it's got to wait for 1, 2, 3, 4, 5 units to be processed, and then it gets processed. And then what happens? Well, it gets back in line, and it's got to wait for its turn in line again. So it's got to wait for, let's say, another 5 units to be processed, and then finally it's completed and it's out the door. So our unit spends quite a bit of time waiting in line because of the lines, the queues are so long. Here's an alternative. Let's say there's no other work in process in the system. This is a low inventory system. Here, our unit gets processed at Work Center 1, and then because there's no line, it immediately gets processed at Work Center 2, and it's out the door. So you can see that there's a connection between the amount of work in process inventory in the system and the lead time in the system. An analogy might be an amusement park. Let's say that you're a unit and you need to be processed, and in order to be completely processed, you need to ride every ride in the amusement park. Well, what happens if there's lots and lots of other units or other people in the amusement park? You're going to spend a lot of time waiting in line for each ride. Now let's think what happens if there's only a handful of people in the amusement park. In that case, you're going to ride a ride, and then you're going to go to the next ride, maybe wait in line for a minute, maybe not wait in line at all, and so on. Well, in which situation is it going to take you the less amount of time to be processed or to ride all the rides? Well, obviously, it's in the lower inventory system. Note that the amount of processing time that you incur in either system is completely the same. You're spending the same amount of time actually riding the rides, but what we've done is we've eliminated all the queue time, all the time that you're waiting in line, simply by eliminating excess inventory in the system.
Is what happens to a tube, sort of a day in life of a tube in the existing U.S. stroller system. First thing that happens is we buy straight long tubes, we put them in purchase parts inventory, we take them out of that inventory, we cut them. If we can eliminate just these inventory steps, we can get material in and out of the system much more quickly. That'll also be a much more responsive system. If you've got 4 weeks of in-process inventory, it's probably going to take you 4 weeks to change gears. If your forecast is wrong and you wind up selling more deluxe strollers than you thought you were going to sell and less of the basic stroller than you thought you were going to sell, if you've got 4 weeks of work in process, it's probably going to take you 4 weeks to adjust to that change in the market. If I've only got a couple of days of work in process in my system, it's not going to take me very long to adjust my production to the new product mix that's being demanded by the market. If work in process inventory is high, then a disruption in an upstream work center oftentimes isn't felt by a downstream work center because there's a lot of in-process inventory.
The U.S. stroller example is also a good application of this concept. If you look at the case and you see what happens to the tubes that they use to make the strollers, they start out in a purchase parts inventory. Presumably they just buy long tubes, put them in inventory until they need them, and they come out of inventory, they're cut, they go back into a work in process inventory until they need it again, and then they bend them and they drill them, and then they put them back in inventory again until they need it in final assembly. And if you look at the case, you'll see that the amount of inventory they have is really high. They have 12 weeks of purchase parts inventory, and they have 4 weeks of work in process inventory. That's a lot of material. Think about the implications of that. For example, if the forecast is wrong, and maybe we start to sell more deluxe strollers and fewer basic strollers, and we use different types of tubes for those two types of strollers, then it could take us up to 4 weeks to change gears and respond to that change in the market. If we don't have a lot of stuff in inventory, then we can change gears very quickly. If we're making stuff to order instead of making strollers to stock, in other words, each customer gets a different stroller, and we have 4 weeks of work in process inventory, then it's probably going to take at least 4 weeks between the time a customer places an order and the time that we can deliver that order, simply because of the amount of things in line, in the queues, thinking back to the previous examples on the previous slides. If we can eliminate all that work in process inventory, we can get strollers in and out of the system much more quickly and have a much shorter lead time from the time we get our customer order till the time that we can ship that order. Okay, so we've talked a little bit about the relationship between inventory and lead times, now let's talk a little bit about the relationship between inventory and quality, or between inventory and variability. Quality and variability are really sort of two sides of the same coin. In a low inventory system, the effects of a problem, such as a quality problem, an equipment breakdown, something like that, are felt very, very quickly. By contrast, in a high inventory system, inventory tends to cover up or buffer against those types of problems. In a low inventory system, we're forced to deal with quality problems, and that tends to improve the quality of the system. Let's look at an example. So here is sort of a graphical representation of what we might find at US Stroller. I guess we might find that if the tubes that they dealt with were green and huge. So we've got our tube cutting department here, and after tubes are cut, they go to our tube bending department, and you can see this is a high inventory system. We've got lots and lots of tubes waiting to be cut over here, and then between the tube cutting department and the tube bending department, we've got lots and lots of cut tubes waiting to be bent by this guy over here. So you might ask yourself, what happens if there's a problem with one of the tubes? You know, maybe it's defective, maybe it wasn't bent correctly, or maybe it was defective before this tube cutting work center ever got it, but they didn't catch the defect, and the defective material got passed on. And let's just say that this unit here, this red unit, is defective. Well, if we've got all this work in process inventory, and this person here discovers a defective tube, they're not really forced to deal with it. You know, it's possible that they might deal with it, they might raise a red flag, so to speak, or, you know, they might just sort of put it to the side and maybe grab, you know, a different tube to work on, maybe this tube. That's a bit of an oversimplification, but that's, you know, basically the case. I mean, it's basically human nature, especially if I've got quotas and things like that, and I'm under a lot of pressure to produce. It's fairly easy for me to ignore, or at least put off dealing with defects that I might encounter from upstream work centers. Let's look at a contrasting situation. Let's look at a low inventory system, and you can see in this system there's almost no work in process inventory. There's almost no cut tubes. This is almost a one-piece flow. Let's say now that this person finishes working on this good unit. They go for the next unit. There's only one unit here, so they don't have any choice, and it's a defective unit. Now what are they going to do? Well, it's a lot harder for them to ignore it because there's no other pieces in the pile. There's no pile of WIP for them to go to. So it's going to be more likely that this defect is going to be felt, that this defect is going to have to be dealt with. This person's going to have to raise a red flag, and hopefully that's going to cause us to go back and figure out, you know, what's creating the problems over here, deal with those problems, fix those problems, and improve the system. Similarly, if this machine breaks down, it's not going to take very long for the work in process inventory here to be deleted down to nothing. Now all of a sudden this person has nothing to work on. Again, that situation raises a red flag pretty quickly, becomes pretty obvious, and we're probably going to have to figure out what's causing the machine breakdowns and deal with that situation, hopefully fix that situation, and improve the reliability of the entire system. In other words, reduce the variability of the entire system. There's a fairly famous metaphor, the boat on the Rocky River, that also explains this point. It explains how quality is required for JIT to function, but also at the same time how JIT drives up quality. So we can think about the company as a ship that's sailing along on the sea here, and rocks are problems in this world, you know, things like defects, breakdowns, etc. But the rocks can be covered up. They're covered up by inventory. So inventory is kind of like water covering up these rocks, kind of like in the last slide, if we've got a huge pile of inventory, so to speak, it's fairly easy for us to maybe ignore a defect. If there's a machine breakdown, we won't feel the impacts of that breakdown as quick because we've got lots and lots of buffer inventory to draw from. So inventory allows the company, the organization, to essentially ignore problems more so than it would if we had lower inventory. If we had lower inventory, let's say the water level was here instead of up higher, it would expose some of these rocks, and the boat's going to sail into these rocks, or the boat's going to have to deal with these rocks. The boat's going to have to figure out how to eliminate these rocks so they're not a problem anymore. And as we solve those problems, we can lower the inventory level even more in our organization. That'll expose more problems. We can deal with those problems. We can get better and better. So you can see how lower inventory, manufacturing situation and even the service situation can drive continuous improvement. Here's another way to look at the same concepts that we've been talking about, and that's by thinking about the economic order quantity model. Just recall that the economic order quantity model wants to balance setup costs and inventory carrying costs. Our holding costs or inventory carrying costs go like this. They increase as our batch size increases. On the other hand, our setup costs look like this. Okay? The bigger our batch size, the smaller our setup cost per unit. And the so-called economic order quantity, according to conventional thinking at least, is the order quantity that minimizes the sum of those two types of costs, and that's going to be where the two curves intersect. So right here. What would proponents of JIT say about this? Well, let's think about what we've been talking about so far. The proponents of JIT would question whether inventory holding costs are really what would proponents of JIT say about this? Well, a proponent of JIT might say that we're underestimating our inventory carrying costs for the reasons that we just talked about, because inventory has some pretty significant non-obvious costs when it comes to impacts on lead time and impacts on quality, as we just discussed in the previous two slides. So if inventory carrying costs are really higher than we conventionally think they are, just based on something like a cost of capital, then our inventory carrying cost curve is going to be a lot steeper. It's going to look something like the one I just drew there. And what would a proponent of JIT say about setup costs? Well, as we talked about towards the beginning of this virtual lecture, JIT proponents say that setup costs don't need to be as high as they are in most conventional operations. There's things that we can do to reduce setup costs, either by reducing the need for setups or eliminating setups altogether. And if we're able to do that, then we can basically shift the setup curve down and to the left in our diagram. So the setup curve maybe now looks like this. So what does that do to our economic order quantity? Well, again, the economic order quantity is the intersection of those two curves. Well, look, now that intersection is here. So we've essentially shifted the economic order quantity for the business to a much lower order quantity or a much lower batch size. I don't think most proponents of JIT would actually do these calculations. I think most proponents of JIT would tell you that it's almost an article of faith that smaller batches, lower inventory is a better thing. But this is a way to sort of to understand JIT using conventional thinking about inventory and about batch size. Okay, so let's go back to our definition of just in time, producing what is necessary, when it's necessary, in the amount that it's necessary. We've been spending a lot of time really talking about the amount, the idea of producing in very small quantities or even quantities of one. We haven't talked very much about the what and the when, and that's how we coordinate production. In other words, how do we coordinate downstream demand with upstream production within an operation system? So let's talk for a few minutes about that. Two really important concepts are cellular production and Kanban. Let's start out talking about cellular production. We've touched on cells a little bit already. A cell you can think of as kind of like a little miniature assembly line that's dedicated to making one part or a few parts with similar processing needs. Cells reduce setup time because we are grouping like parts together to reduce the need for setups. But it's also really important to understand that cells also improve coordination within our operation, within our facility. Here's a picture of a work cell, classic kind of U-shaped cell. And you can see that if you worked in this cell, you would have a pretty good understanding of what's happening other places in the cell. Employees might work on the outside of the cell, but it's more likely that they are stationed on the inside of the cell. In a bigger cell, we would definitely want to focus on that when they're stationed on the inside of the cell, because that makes the employees closer to one another and improves their ability to communicate with each other, to coordinate with each other. It also means that if one person gets behind, maybe another person can hop over and help that person out to keep everything in balance. Because it is essentially a little miniature production line, we can essentially have one piece flow, between units in the cell, and there's no need to take material outside the cell, put them in inventory, and then bring it back later, to be processed by another worker. So cellular manufacturing, just really as a function of the layout, inherently gives us a real high level of coordination in our operation. An alternative to coordination using cells is coordination using Kanban. Kanbans are especially appropriate when work centers aren't adjacent to one another as they are in cells. In other words, we might have a situation where we can't group work centers or workers so that the downstream process is immediately adjacent to or next to the upstream process. If we're in certain situations, there might be quite a bit of distance. There might be multiple floors or a whole lot of linear space between operations. If that's the case, then a Kanban can be a very effective technique. In fact, you can even use Kanban to coordinate with suppliers who might be a couple of towns over or even in the next state. Kanban literally means sign, and a Kanban is a sign or an authorization that's sent by a consuming entity or consuming work center to a supplier, an internal supplier or an external supplier. And you can think of that sign as a sign to produce or an authorization to produce a certain number of a certain thing. So let's explain how that might work. There's several different types of Kanban signals that we can send. Three very common ones are a Kanban card, a Kanban square, and a Kanban container. So let's talk about at least two of those. So let's say we're making bikes. Bikes are kind of a good thing to talk about because most of us have a good sense of the different parts that go in the bikes, at least the main parts that go in a bike. Um, so how might a Kanban container system work to coordinate bike production? Well, let's say the last step in making our bikes is final assembly. And let's say that we keep 5 racks of 10 front wheels each um, in final assembly. And let's say those racks are on wheels. Each rack has 10 slots, so it can only hold 10 wheels. Can't hold more, can't hold less. At least it can't be overfilled. Whenever we consume a rack in final assembly, we send that rack back to the work center that assembles the wheels, and that serves as a signal to produce 10 more wheels. Of course, if we're using 3 or 4 or more different types of wheels, the type of wheel would have to be identified on the rack. So the wheel assembly people would receive that signal, they'd receive that empty cart, and that's essentially their signal to produce 10 more of that type of wheel. When they produce them, they fill up that rack, they transport that rack back to us in final assembly. We can think about what happens kind of one level down. The wheel assembly folks that we've been talking about might keep baskets of spokes, right? Maybe each basket holds 280 spokes. So they're emptying out those baskets to create wheels. And when they empty out a basket, the basket would be sent back to a fabrication department that cuts wire into spokes, or maybe even an external supplier that makes the spokes for us. And each one of those baskets serves as a signal to produce 280 spokes. And on it goes, back and back through the system. One department, the consuming department, basically sending these little pull signals to the supplying departments to produce. There's kind of a graphic representation of the system. We can think of the system as empty containers falling back, and those containers being filled up, being sent back to the consuming entity, and at the same time, containers going a step further back, and full containers coming back, and so on. Of course, we could draw, more and more layers here, and of course, there are more and more layers, going out this way, because it takes more than just the wheels to make a bike. So it's a very simple, but incredibly effective way to coordinate operations. An alternative might just be an empty square on the floor. So if we have Work Center 1 feeding Work Center 2, Work Center 1 is producing, putting material in this square. Work Center 2 is producing, is taking material out of the square, finishing it off, and maybe sending it out to the market. So anytime there's an empty place on this square, it serves as a center for Work Center 1 to produce more. This square might be set up so that it holds exactly maybe 9 pieces of work in process material. So anytime there's an empty square, it's a signal for these guys to produce. A really nice thing about a Kanban system is that it limits the amount of work in process inventory in the system. Earlier in this virtual lecture, we talked a lot about the advantages of a low inventory system, and it just so happens that Kanban enables us to have that kind of system. It was one of the factors that enables us to have that kind of system. How does that work? Well, if you think about the examples that we've been talking about, where does the permission to produce come from? Well, the feeding work center doesn't produce until it has an empty Kanban. If all the Kanbans that it's supposed to fill up are full, then it doesn't produce any more. So that naturally limits the amount of work in process that we can have in our system. So Kanbans are sometimes referred to as queue limiting devices. So Kanban is kind of a dynamic, self-regulating way to make sure that the system doesn't produce too much in-process inventory. Again, if all the Kanbans that I'm responsible for filling up are full, if all the spaces in that Kanban square that we drew are full, I don't produce anymore. I go do something else. Maybe I do some preventative maintenance, I do some cleaning, I engage in some kind of training, but I don't just keep producing inventory for the sake of producing inventory. Okay, so far we've been primarily talking about internal operations, but many companies have thought about how to implement JIT between companies. In other words, between a consuming company and a supplying company. And many companies have been very successful with it, and they've reaped a lot of the benefits that they might get internally in these intercompany relationships. If you think about what JIT would mean for dealing with suppliers, it would mean having no raw material inventory or minimal raw material inventory. That means that the material that I get from my suppliers, if I'm not going to have a bunch of purchase material from my suppliers on hand in inventory, then I have to have a steady, predictable supply from my supplier that's high quality. In other words, I have to be able to count on my supplier delivering when they say they're going to deliver, and I need to be able to count on every piece of material that I get from my supplier being the quality that's required. It also implies receiving material in small quantities or small batches that are more or less paced to match consumption. Perhaps that's with the Kanban system, where I'm actually sending empty containers in a truck back to my supplier and they're filling it up. Perhaps it's some other kind of system. So, many companies, again, Toyota is a great example, have found that there's some things that they can do with regard to supply management to help facilitate this. One is supplier development. If you're a bigger, sophisticated company, there may be a lot of things you can do to help develop your suppliers. It might be smaller suppliers to bring their quality level up, to make them more reliable, and so on. Some companies certify their suppliers, so they go and take a very in-depth look at their supplier processes, so they know that they can count on their suppliers to keep their commitments with regard to quality, with regard to timing, and so on. Communication with suppliers is also very important. So this all sort of implies that I'm probably going to have a more close, more intense relationships with a smaller number of suppliers than I might have than I might have otherwise. Many of us have heard terms like supplier partnership, strategic suppliers, those types of things, and being in a JIT relationship with your suppliers generally necessitates that level of involvement and that level of commitment with suppliers.